All right. I think the record is now on. So let's do this. Okay. We are going to try to draw. This example is rather easy because I don't have the more difficult one at hand. But you would have it on your say tutorial session or active session. Well, oh, let me remind you one more thing, because we missed the active sessions last week due to the APEC, and we are going to have one more tomorrow. I don't know if it's going to cover all you ever need, because it's just 1 hour. However, I don't have any class to go to anymore. So if you have free time, you can extend your active session, but you probably have a class yourself, right? So you need to think about it, whether or not you need more hours for your active session. Next week is a reading week, because I think hopefully chances are we are going to finish our class today. So everything will be done by today. So if you want the active session, let me know. You can use some time to do it. But you guys, final exam are coming thick and fast, right? Our exam is on the 8th, if I'm not mistaken. So, however, yeah, with that in mind, and if you have a problem with the acquisition, you can turn on another one. Anyway, if it is your reading week and you don't have anything in your system, not a good idea. So you may want to turn some few hours of your reading week into the active session with me. Okay, we can do it on Wednesday in the class time, because you're supposed to be free, right? But if you don't want that, you'd rather spend some time watching some movies, listening to music, enjoy yourself before you go into the battlefield with empty head. That's fine, right? But if you want, let me know when we can meet. Okay, so let's go. Let's turn ourselves back to our business. Now I need to go into the right folder and try to enter the right. You know what? I'm really glad something like my accent, because I kind of mix the British accent with my pronunciation, right? Just to make it a little bit more classy, right? I can also speak a few more accents if you want, just for the sake of not getting bored. All right. But you would end up laughing, so that's why I don't do much of the change accent anymore. Yesterday, you're gonna do this. Yesterday, my daughter called me, and I picked up the phone and I used a very strange voice talking to her. Hey, what are you? What do you want? Like that, and it just so happens that her friends are nearby, and I don't know how they could all hear our conversation. She must have turned on the speaker, like that, or laugh. Hey, your dad is cool. I don't know how cool is that. Just change your voice. Anyway, okay, we're gonna try to do this. So this is a new problem. So let's try to write down. Okay, this is your beam. Look like this. All right. And I give you a roller. Oh, and this becomes the indeterminate structure, right? But I give you the internal hinge. So when you have the internal hinge, it means that generally this structure becomes a determinate one, correct? Because now you have an extra equation, knowing that this point has moment equal to 0. And so I give the length 6 meters here. And we have a point of interest here at the distance 6 meters. Calling that point C. So this accent okay? Maybe? Still okay? Oh, but maybe we could try some action. Like, Texas. Like that. But I don't like that. Anyway. So let's go on, and this is 4 meters. Okay, it's a little bit too short, not drawn on scale. My apologies. Small. Okay, let's enlarge. And again, we call this point A, point B. Let's see that it should be D. We're going to try to draw the influence line or the following design functions. The first one is RA. Yeah. Okay. Yeah, right. Save all mistake. Thank you. RA. The second one is VB. And then VC, RD, and MD. See what happens. Okay. Can I what? You speak through the mask and I'm forward, I'm far away from you. I can't understand. No, it's not. It is. I didn't. See, are you trying to kill me by the shock? You know, that is a very scary thing because let me tell you a story. Long time ago, when I was doing my master's, you know, there used to be a live session like this, and then the professor was teaching, right? And because they got two campuses, so he was doing the live thing to another campus. And then by the end of the session, the guy who worked with the equipment said, "Professor, I'm sorry, we could not do the live to another campus, so you have to do it again from the beginning." And then he said, April Fool's. You know what that is? April Fool's Day, you're supposed to tell a lie, right? And then the professor he was shocked, you know, because you got to teach again like for 3 hours. And he said, "Oh, good one." Yeah, so you were doing that on me. Anyway, so I'll give you guys a few minutes to try to finish this, okay? This would be interesting because now we have a little bit more complex structure. And what always happens that you guys always forget that you can apply the unit load anywhere to try to solve this. Okay. So let me go quickly, otherwise I'm afraid that I may not be able to finish. Okay. So now for RA first, you know what's gonna happen. We're gonna let RA go free, right? But we have a hinge. So what do you think is gonna happen? Yeah, RA we just go up. But this is a hinge. And it will go up like that. But when you try to push the portion BD up, that is a perfect cantilever beam. So when RA is free to move up, RA cannot move BD portion. And therefore this becomes the influence line of RA. And when you try to look at the structure, you see that when your unit load reaches B and moves beyond point B, kind of like this, when you do this. When the load is between A and B, some reaction will be on B, right? Sorry, it's got R with me. Right? No. But when the unit load moves beyond point B to between B and D, this is a cantilever beam, and you can forget about the fact that you have it. It becomes a typical cantilever beam. So it makes sense to have the influence line that looks like that. Okay? And B is just another point. So when we try to say, let the shear go free. In fact, you remember, I grade the second student over the regular program. And, many of them do not realize that this is just a sign convention. So we move it down. We have a hinge here, so it's just going to go down. Like that. But again, when we move to BD, you meet the solid part, so it cannot move. So it becomes the influence line of the shear at B. Okay. Wow. You know, generally I would lock door. If we have a typical on-site class, you're gonna have to wait for the next session to get in. Barging in late will destroy my concentration and your friends as well. But this is the last class, right? Can't do anything. So this is the shear. And when you think about how the load will affect your function, you know, let's say okay, you guys are taking notes. I'm going too fast, maybe. I decided to add the content, and now I'm a little bit afraid that I may not finish the whole thing, so I'm just going fast a little bit naturally. So okay, now guys are catching up, right? So when the unit load is moving towards B, you know the shear B should increase, right? Because you now the shear section B is under greater load when the load moves closer. In terms of shear, so it should keep increasing until it passes point B. Again, there is nothing that is going to tear point B apart. So as soon as your unit load moves beyond this, the shear becomes zero. So it's my wish that you would see the behavior of the structure rather than trying to use the Muller-Breslau method and fail. Well, once you see how the method helps you, you should be able to relate what you have here with the actual behavior of the structure as well. Okay? And VC now. Oh, interesting. Now VC is beyond here. So let me try to draw. So point C is now here, okay? So when I want to free point C, on the right should go down, on the left should go up. So what's going to happen to the left side here? What's going to happen to this side? Remember, you have a hinge. So when it's going to go down, what does your imagination tell you? How it is going to move? You have two hinges now at A and B, correct? So things should fall. It's like a typical hinge. Think about the door. So this guy should come down again. But here, you don't have anything anymore. It's just a solid structure with the freedom to move with the shear on the right. So this should look like this. Now, again, when the load reaches the right side, you have another cantilever. And, you know, there is nothing on the left side of your C, of your section C at all. So when the load passes point C, again, we should have zero shear. Because now you focus here and you see you have a perfect cantilever beam. Right? When the load moves past point C. So the left side doesn't matter anymore. The shear becomes zero. And as a result, this becomes the influence line of the shear force at C. And think about it. When you have this, you should always try. I think you guys are not looking very happy, so I'll slow down. Okay? It's time for you to use your imagination and talk to the structure a little bit more, right? Yeah. Okay. So let's slow down a little bit. Any questions? And let me remind you again that if you cannot read my handwriting, you must notify me immediately. Okay? That is imperative, means urgent and important. Okay? Now, guys, let us try to relate the shear at C to the behavior again. So now I move this and just get caught up with the color red, so I'm just gonna move together. Yeah, I know it. Damn it. Now it's impossible to split it, so that's just to be right. Damn. Okay, so let's say we have a load, yeah, again. When the load moves between A and B, you know, some load is going to be transferred on the B. So it's just like a shear at B. So the more it moves closer to B, the more shear at B is going to have, and therefore it's just going to have to increase the shear at C as well. And when this load moves beyond point B, between B and C, now you have a cantilever, right? Because portion AB doesn't matter anymore. When the load is here, what you have is this. Because this load will not send any effect to the portion AB. It becomes a cantilever beam. Portion AB doesn't have anything to do with your structure anymore. Once the load moves beyond point B, you should see the behavior like that. And therefore, you have a perfect cantilever beam like this. And that means if I ever cut any section on this, the shear between the load and the support is a constant, right? Think about your shear force diagram. Let's say if I'm here, the effect of this load is going to be cut. That's going to cut through this. It's going to be the load itself. Here, load itself. That's why the shear at C becomes a constant. Once this load passes point B, again, and moving towards point C itself. So you have a constant shear, right? Think about your shear force diagram of this structure. And again, once this load moves past point C itself, it becomes a cantilever beam. That's why we have a zero shear at C. It makes sense, right? This is how we use Muller-Breslau to the extreme, and you're going to have a lot more fun with the examples. But I think I have a few. Okay, and now RD, right? What's going to happen to RD? When you want to move RD freely, RD is here, right? You know what's going to happen. Think about it. Because just a similar way, in the way I talk about the shear here. Once the load gets beyond point B, you know, RD will become a constant, right? Can you see that? When the load moves past point B, your RD becomes a constant. Right? Because you now have a structure that looks like this. So your reaction is always equal to that. Right? It doesn't hurt to go back and try to understand the structure rather than applying Muller-Breslau blindly. Okay? So now, coupled with a little bit of knowledge that I can see that, you know, RB is going to be zero when your load sits on here, right? Likewise, when I try to move this, what happens is that because we have a hinge here, so portion AB will move up. And then the rest will come constant. So this is influence line of RD. See? Because once the load moves past point B, you have a constant reaction, which is represented by this portion. Right? Now, generally, one more thing, you know, in fairness to me, this is the first, maybe one of the very first years I write a lot. Because generally, I don't write that much. I will speak, and it's your duty to take notes. But this year, I decided to write more, so that for those of you who don't have very good listening ability, we have a chance to get to see things. And now I have a complaint about handwriting. Yeah, you know, you win some, you lose. So this is the region of, say, constant RB, right? What RD, right? Not B. This is D. There's a dog, right? And now, boom. Okay. Please stop me anytime you have a question. Don't let it go by, okay? Just ask immediately before you forget. Hey, you guys need more light at the back, and just come and turn it on, okay? Okay, what about moment now? The moment is going to happen when we will try to let this guy go free like that, right? So Now we have a hinge at D so that this could move. We have a hinge at B, we have a hinge at A. So everything will fall, right? Because we have 3 hinges. So you can imagine that it will go like this. Now, let's see if it makes sense. But you guys are writing first, right? You know, I thought about that day a lot when I got COVID, because the week before I went down with COVID, we got a lot, we got more students in the room. This more than this. That was the day with the most attendance. You know, everybody came in here and everybody went where, and then I got COVID. So I taught from home for 1 week. And the week after that I came, it was like disappeared the entire class. So sometimes, you know, this is on record. I can tell you the story about the collapse of the building. My teacher, one of my very beloved teachers, he said, if you have something collapse, you need to have 3 bad things. 3 bad things have to happen. First, bad design. Second, bad construction. Third, bad luck. So it takes a lot for one building to fall down. And that hotel that Ajahn Bharat mentioned yesterday was at the Korat province. It collapsed when I was a 4th year student. And I did not go. The department organized the tour to the site. I didn't go because first of all, I can say that I don't want to. Second, I got things to take care of because I was the vice president of the exhibition, engineering exhibition. And so my friends came back and said they smell rotten water all over the place. More than 100 people died. You know what happened to the building? There was a cafe underground for lunch. And there was one troublesome one blocking the view of a singer. Well, you know, audience can't see a beautiful singer, so they wanted it removed. Then when you remove the column, you know, generally, what happens? If you have a building like this, and you have columns coming, and you say, okay, we have a lot of floors like this. Say, you know, this guy is blocking a singer. So okay, we're gonna remove it, right? Fine, no problem. So what happens? You can do it. It's not a problem. You need to make this beam very strong. It's a transfer beam. And then it has to be able to transfer the load of this entire column to this distance. In came the first thing, was a bad design, because the guy who designed the connection between the beam and the column, they probably didn't do it properly. He wasn't a real engineer. He was like the 4-man turned engineer. Okay. Second, I bet the construction may not go very, very well. But on that, on the particular day that the accident occurred, you know, we generally store water on top of the building. Do you know why? You got a class with the Ajahn Rudi, you should know why we store water on top of the building. You know why, right? Because of the head, so that water can flow down very easily. You should just pump it up. And then when you use it, you just use the gravity. And on that particular day, the water tank was full. Not only that, there was a small conference with hundreds of people in the conference room. And so the live load was full. And you know what? They said there was a sign that these columns were about to collapse, because the cracking occurred before, but nobody paid attention. And when the collapse occurred, you know, the concrete just burst out of the column. Because in the concrete column, you would have reinforcement like this, right? No concrete left in the stir-up area at all. It's complete failure of concrete. It takes a lot for the building to fall. I have more stories, but I don't wish it to be reported. It involved my whole company. So, let's leave it at that. Okay, this has nothing to do with that. So that we can see. Okay, so here, think about the moment. We go back to the load again. If you can see the shear, when the load is here and moves toward B, the shear at B is going to keep increasing. And the shear at B will go to the portion BD. So when the magnitude of the load keeps increasing, the moment at D should keep increasing. And the load will be maximum when the load itself reaches B. Right? And from this point onward, the load is the same because it is now on BD, right? The shear on BD will remain constant. However, this time the moment will keep reducing because the moment arm keeps reducing as the load moves towards the support itself until it reaches the support. Your moment arm becomes zero. So that is why we have the bending moment diagram. The influence line of the moment at D. It looks like that. It increases at first until the load reaches B, and then it reduces because now your load becomes constant, but it moves towards the support, and thus the moment arm keeps reducing. So it makes sense. And now the next question is, how much? This is one, right? No need to discuss one. This time you use too much of your intelligence to understand this. It's a good thing because you see this for the first time, so it can tire you out because you think a lot. Okay, it's only natural. Now, this value would come from the fact that you load the unit load at B, right? Because this is where the maximum moment occurs. And what's this distance? I think it's 10, right? So what's the moment? Oh, it's 10, right? So this is 10. It's not 1. Okay? Do you have any question on this? No? So hopefully crystal clear. Is it? Oh yeah, right. Yeah. Yeah. I shouldn't expect anything less, right? Guys are the most brilliant in the world. So I think it should be crystal clear to you. Okay. I put my glasses on for no reason, like a prop. Because I need to go back here a little bit to demonstrate the use of the influence. Remember the last time we talked about the fact that you can multiply the influence line with the magnitude of the point load, or you multiply the magnitude of the uniform load with the area of the influence line that we cover. That's the first function. Seems like a bit British today, right? I hope. Okay. Anyway, now we are going to focus on another thing that is called the placement for maximum effect. Oh, no. Yes, that's wrong. Okay. This is actually the real use of the influence line, because remember our too small. Remember the loads. Ooh. So first of all, we need to be able to figure out the fact that when the load moves around, what is going to be the most critical position that it is going to give the most critical value of the design function to us. Right? Now, we're going to start by looking at the first thing. Generally, let's say if I want to know, we have the moving loads coming in, a lot of them moving towards the beam like that. Okay. Sorry. When the load moves toward the beam, and then I say, I want to know the shear at C. What kind of loading position will give the largest, biggest magnitude of shear at C? Now, if you don't know anything, you'd say, we're just going to have to keep on trying every position, right? Let's say we have 200 loads. We're just going to put load number 1 on C, load number 2 on C, 3, 4, 5 until we reach 200. But that would be the Stone Age, right? If you have something like that. And even though we have computer now, we are in the age for that, we still have a method. So the first one we call the method increase decrease method. And here, okay, let's say now I actually love to see the load moving from right to left, but now it's moving from left to right. Okay, so let's say I have a load P here. You can see it moves to the right, goes up the slope of the influence line. Okay, at position number 1 or point 1, we have the coordinate x1, y1, and point 2, we have x2, y2. The x would be the distance or the location on your beam, correct? And the y would be the height of your influence line. And you know, when we talk about the coordinate system, xy, for example, do you know its name? Do you know the name, the official name of the coordinate system xy? Want to try your luck? Now you talk, look at your friend. I should look at him. Oh. You want to try your luck? Do you know what it's called? XY coordinate system? It is called Cartesian system. Right? It tends to go like that, my hand, right? Yeah, right? So it's because I'm talking and writing at the same time, and I write what I talk, so I don't have to feel like, oh, Cartesian, it goes like that. And when you don't catch up, you don't ask me, what is this? I'd say, how the hell would I know? Because I was talking and writing at the same time. You need to ask, you know? Okay, anyway. It's called Cartesian system. And there are 2 spots, so we call it coordinate. If we talk about 1, it becomes ordinate. Okay? So right here, if we talk about the height of the influence line, we can call it ordinate. And now, from the use of the influence line last time, we say that the design function can be equal to the load itself multiplied by the height of the influence line. Correct? That will give you the value of the design function. The load multiplied by the ordinate one. At point 1, you have P multiplied by Y1. Point 2, you have P multiplied by point 2, right? Remember, load P moves from point 1 to point 2. So now I can say delta F, the difference of the design function when the load moves from point 1 to point 2 is going to be equal to the load multiplied by the difference of the height. Let's remove that. Right? This is the difference of height. You can call that delta. You can call that dy. You can call that gradient. But it's just y2 minus y1, right? The height here. So I remember first bad experience in the university, in the physics class, when all of a sudden the guy started talking about gradient. I never heard of that word before in my life. What the hell is something like this? What the? So, here is the difference. But now, let me catch your focus again. We are talking about the change of the load. Now we want to know when the load itself moves, how much the design function changes. For example, if he moves from point 1 to point 2, how much my reaction will increase, or how much my shear will increase. Not the magnitude of the reaction or the shear itself, just how much it changes. Okay. So generally, I never did this before. I never done this before until this year. Last year, this year I have done a lot more. So that's why I don't have understand how much design. This is function, okay? Changes. Not the design function itself. How much it changes. That's why it is called delta. The difference, not the force itself. Okay. We all know dy by dx by heart, right? Love it, you hate it, you know why. Dy by dx is simply the slope, correct? So we're talking about the change of the slope in y direction. The change in the distance in y direction versus x direction. We call it the slope. Dy by dx would therefore become y2 minus y1 and x2 minus x1. And I now can replace this, right? Y2, y1 here by this equation. Okay, I can move x2 minus x1 on this side and replace it here. So this equation becomes the force multiplied by x2 minus x1 multiplied by the slope. X2 minus x1 would represent what? The distance that the load moves. We are interested in point 1 and point 2. We should be able to obtain the distance that the load moves very, very easily. So this one is easy to find. It's just the distance the load moves, right? Here we go again, my handwriting, because I write what I say. And I'm trying to improve it, and surface makes it a little bit harder. Like trying to dance on thin ice, writing on iPad. Believe me, you've been here for a long time, but not on site. If you're on site, you see some instructors can't write on the board and keep the line straight, And you guys can do it, and you find yourself, your letters keep going up, right? It keeps showing up. Maybe you've seen that at school, but I don't. My lines remain straight because I need to practice it. I hate that. I hate the fact that somebody write the board and the letters keep going up. So beautiful. I'm not going to do that myself. And now that's one hardship of writing in the vertical direction because the board is in vertical direction. You guys write in the horizontal direction. Very easy. Now, here comes the iPad. And the surface is slippery. So just ready to go like that. Another fact. Anyway, so here is the distance that the node moves, which is easier, a lot easier to obtain. And here becomes the slope of your influence line, which again, very easy to obtain. Yeah. That's the main reason, because if you use this equation, what it means is that you have to calculate the height of your influence line every freaking time, right? But here you have the influence line, you know the slope and the distance just comes naturally. That's why we changed it. And therefore, in the end, we have now the formula that can help you determine, not determine, whatever. It's determine. I can write down D and then determine. Pronounce like that, and they will understand. Not me. Determine. Sorry. I have to be dramatic, otherwise I just cannot get into my groove. I don't know why I have to be crazy like this, but I just couldn't help myself. Okay? So this should help you determine the change of the design function. Not, too loud, right? Not the design function itself. All right. Can tone down the energy. Do the amplifier is there. Ample. You know what ample means? Ample. Ample. You know the amplifier, right? Yeah, but you don't know the word ample. Ample is an adjective. It's a lot. So to make it a lot, you change it to a verb, so it becomes amplified. And the things that amplifies becomes amplifier. See? So the things that only amplify without control, we call that pre-amplifier. The amplifier that you can control the volume, we call that integrated amplifier. So we talk about the stereo now. Okay. Sorry, it's going out off topic again. All right. So here we go. That means if you want to determine the change of the design function, you have the load you already have. You need to have the distance that the load moves and the slope. That's the first method, and that is the break. Okay. Any questions? It's best if you see the example, but this is the concept. Okay. Questions, please. No question. Okay, so I'm just gonna write. Stop recording. Yeah.